I've actually known Rachel for, must be 20 years now, and seen the exciting research on impacts that's come out of UEA and the Tyndall Centre. And so today we're going to hear about this project from phase 1 of UKCR and really get a first glimpse of the results. So Rachel, over to you.
Thank you, Jason. I'm just going to share my screen.
That looks great. We can see that.
Thank you, Jason. So it's a pleasure to speak to you all today, and thank you very much for taking the time to listen. The project Impacts and Risk Assessment to Better Inform Resilience Planning IMPRES is led by the Tyndall Centre UEA and is nearing completion. And in this webinar, we will explain how we have used our funding to improve our ability to project the magnitude and extent of some important risks and the uncertainties therein. The risks, that is, that climate change poses to the UK in the future. We focus particularly on methodological improvements to the simulation of heat stress, also looking at drought, flooding and water stress, risks to biodiversity, ecosystem services and natural capital. The project is very much a team effort with major contributions from Alan Kennedy-Esser, who will speak after myself, with Oliver Andrews at the University of Bristol. We'd also like to thank Dan Mitchell for his assistance. And the presentation will end with a contribution from Jeff Price at UEA, who will speak on our biodiversity and ecosystem services work. The improvements identified by IMPRES are being taken forward in the newly funded project OpenClim, which Jason mentioned, which is also led by the Tyndall Centre and funded by the UK Climate Resilience Programme. The project's academic achievements are that it has produced some preliminary model-based UK climate change risk assessments for drought, heat stress, water scarcity and fluvial flooding. These are the starting point for the project. They're not driven by UK CP18, but by the outputs of a model called ClimGen that produces 50 by 50 kilometre resolution regional patterns of future monthly climate change anomalies compared to an observational data set from the Climatic Research Unit for 1961 to 1990. And these come from combining global temperature time series for the 21st century from GCMs with recent observational baseline data. Having done that, we then went on to identify how we could improve or adapt these modelling approaches, mostly which were originally designed for the UK scale, to focus on the UK and to use UK CP18 to drive them. And then having done so, we applied those improvements in some of the risk areas, most notably heat stress, but also biodiversity and natural capital, and made some new projections of heat stress in the UK. We've produced some journal publications, which are presently in review or in preparation. Our methodological recommendations informed the development of the successful OpenClim bid. And we've benefited from a synergistic relationship with a sister project funded directly by BEIS, looking at the projection of climate change risks in 6 countries. We've produced a project infographic for use in future stakeholder workshops, such as the upcoming OpenClim workshop. And we've been able to develop and reinforce some links with key stakeholders in government-devolved administrations, WHO and the wildlife trusts. And hopefully we can begin to engage with some more of you today. This is an example of our preliminary risk assessment. The projections here are for exposure to fluvial flooding and refer to an average over a simulated future 30-year period, 2086 to 2115, across a range of scenarios with different levels of warming by that time period. So here we first calculated the depth of the worst flood in the past 100 years in each grid cell, which is called Q100. And we calculated then the additional exposure of people to floods of this magnitude or greater in that future 30-year period. And we compared the case where the population in the UK remains constant and another scenario in which it increases, according to a global scenario known as SSP2, for those of you in the know. Risks are seen to increase in both cases with quite large uncertainties due to differing patterns of regional climate change. But we notice that climate change seems to dominate the impacts, with population changes having a smaller effect. Now, this modelling is based on CMIP5 projections, coupled with a flood inundation model and a hydrodynamic model. And this is more advanced than previous UK-wide projections. However, the spatial resolution is 50 kilometres here. In open CLIM, we will increase it to 12 or 5 or 2.2 kilometres. And we will also be able to include most of the smaller basins in the UK. This result that I just showed you, because of the coarse resolution, includes only 15 of the basins. So moving on now to look at drought. Here we again looked at the population exposed annually by the end of the century. We find again increases in risk, strongly affected by both climate change and population change. The indicator we used here is SPEI 12. That is an indicator which includes not only the change in precipitation, but also looks at potential evapotranspiration, and that is important to include because this increases greatly with climate change. We made some methodological improvements to the drought analysis by looking at a very wide variety of metrics and how they differ in different land cover classes in the UK. Jeff will speak about this and then go on to talk about the work on biodiversity and natural capital. Next to speak will be Alan Kennedy-Asser from Bristol University, and he will talk about how he evaluated the UK CP18 climate products at different spatial scales to assess the suitability of these products for understanding future summer temperature in the UK and heat stress extremes. And then how he looked at how heat stress metrics and thresholds could best be chosen to be most appropriate for the UK. And finally, his exploration of future extremes of summer temperatures and heat stress in UK CP18. I'll now hand over to Alan.
Yeah, Rachel, thank you. So as Rachel said, I'm Alan. I'm based at the University of Bristol, and this work on heat stress was stuff that I did with Oliver Andrews, who was the IMPRES co-I at Bristol, and Dan Mitchell. And these were our three research objectives. So Rachel, if you could just flip to the next slide for me, please. Thank you. So to do this analysis of heat stress and temperature extremes, we were interested to know how UK CP18 would simulate these variables across the UK. So I'm sure lots of you know lots about UK CP18, but for those who maybe have not heard of it before, it's a whole suite of model simulations produced by the UK Met Office, and it can be roughly broken down into 4 subsets. So we've got a global GCM subset of simulations run by the UK Met Office at 60 kilometers resolution. Within that global subset, there's then a nested regional model at 12 kilometers resolution, an ensemble of those. And within that, there's then this local scale convective permitting model, which runs right down to 2.2 kilometer resolution. And as well as that, included in the UK CP18 package, there are some IPCC class CMIP5 models, which were performed by those simulations were carried out by other international modeling groups, but they're included in UK CP18, so we can compare the UK Met Office's model to these other international models. To do the evaluation, obviously we needed to actually compare the models against something. So these simulations all started in either 1980 or earlier and continue through to 2080 or later. But for the historical period, we compare that against observations from HAD UK Grid, another Met Office product, and ERA 5, which is a reanalysis data set from ECMWF. If I get the next slide, Rachel, please. And just one other thing to get everybody on the same page in case you're not sure what I'm talking about. So heat stress, what we mean by that, it's sort of like the feels like measure of temperature. So the temperature that our body feels is not just necessarily the absolute air temperature, and things like humidity can be important. And the reason for that is because our body's main way of controlling our temperature is, when we're hot that is perspiration. So we'll sweat and droplets of water appear in our skin, it evaporates off, and that cools us by latent cooling. So if you've got very high humidity, the evaporation of the sweat is less efficient, so your body is less efficient at cooling itself, and so your body can become stressed in the heat. And this eventually can lead to things like heat exhaustion, heat stroke, and eventually can lead to death. Metrics of heat stress generally include temperature and the humidity components, but they can also include things like solar radiation and wind speed. In this research, I'm only focusing on sort of simpler metrics, which are just using temperature and humidity related variables. So I look at 3 in particular. I've got the apparent temperature, humidex, and simplified wet bulb globe temperature. And those are just a linear combination of temperature and vapor pressure, which is a measure of humidity. And they increase, the amount of importance of vapor pressure increases as you go down through those metrics. And just one other final thing to note is I'll be talking about summer temperature and heat stress extremes, and I'm taking the summer as the 1st of June to the 15th of September, in line with what the heatwave plan for England uses as the heat alert period, or whatever they call it. So next slide, please, Rachel. Rachel, can I get the next slide, please?
It's not working. I can't, I'm pressing page down and nothing's happening. I shall stop and start the share again.
Sure. This is the moment that we'd normally ask you to talk amongst yourselves, but it's a bit awkward really when it's all via the internet. Get the questions coming, fire them into the Q&A there.
Alan, just while we're waiting for the slides to come up again, one of the topics of interest is around understanding what bias correction was carried out in the study.
Yeah.
Do you want to mention that just briefly, and then we'll get back to the slide set?
Yeah, sure. So in the work that we're doing, because we're really focusing on an evaluation here, we haven't done bias correction because we actually want to understand what those biases are, and we want to know in what aspects UKCP18 is performing well. So for the results I'm talking about here, we have not bias corrected the stuff, but we'll obviously be considering that sort of later on down the line with the OpenClim results. So just to go back into the presentation here, oh sorry, I should also say with the bias correction, that's just for this work specifically on heat stress. I know some of the other folks in the IMPRES group have already done bias correction stuff. So anyway, back to these results. So our first objective, as I said, was doing this evaluation of UKCP18. This is an example of one of the figures from our paper and review. This is just a subset of it, and it's kind of the same format as what you might have seen in an IPCC report. And what we've done is we've taken 6 different climate variables and heat stress metrics, which are shown on the y-axis there, and we've looked at the relative error across the whole of the UK, so the root mean square error, for those 4 subsets of UKCP18 that I mentioned previously. So the GCMs, the CMIP5 models, the RCMs and the convective permitting models, and we've taken the ensemble mean for each of those. And if you see a blue color in this, it shows that on average, those simulations are performing better than the average model. And if you see red, they're performing worse than the average model. And the reason there's two triangles for each variable and kind of model combination is because we've compared against both observations and reanalysis data. And reassuringly, for the folks at the Met Office, I'm sure they've probably seen stuff like this before, but the UK Met Office model is doing a really good job for the UK in terms of these summer heat stress variables compared to the CMIP5 models. So you can see that by the fact that GCMs are all quite blue, whereas the CMIP5 models are all quite red. What is also interesting to see for this sort of work, looking at heat stress, actually the impact of increasing the model resolution is less obvious than it might be for some other variables. So if we compare the GCMs to the RCMs and the CPMs, there's actually not that obvious an improvement in model resolution, in model performance with resolution. It depends a bit in terms of what variable you're looking at and what data set you're comparing against. Obviously, higher resolution would be really important if you were looking at something like urban heat islands. That's not something I've specifically looked at with my research, but in that case, you would want to be looking at these higher resolution models. However, what this shows is if you're just interested in sort of larger scale regional or UK-wide changes in terms of heat stress, actually the global and the regional models do a pretty good job and would save you quite a bit of computational time if that's what you're interested in. And a final thing which we learned from our evaluation, you can't actually see it from this figure, but we got it from other bits of analysis, is that actually the heat stress metrics generally have lower errors than temperature variables alone. So when you combine this vapor pressure into your heat stress equations, actually it means the UKCP team does a better job of recreating observations than just looking at temperature alone. Can I get the next slide, please, Rachel? So the second objective that Rachel mentioned was that we were interested in thinking about different heat stress metrics and their applicability for the UK, and also thresholds for what we would describe as dangerous or impactful levels of heat. So as I say, all three of those metrics that we were using basically combine temperature and vapor pressure. So I was able to plot up data in the example of this figure in this temperature and vapor pressure space, and different heat stress metrics and the thresholds that have previously been used in global research are shown by the grey sort of dashed and solid and dotted lines on the right hand side. So the different lines, whether they're dashed or solid, relate to the different heat stress metrics. It doesn't matter specifically which one's which. The important thing here is that the paler grey lines for each of the three metrics show what was described as slight heat stress in this Zhao et al. ERL paper in 2015. And the darker line refers to their definition for moderate heat stress. And then I've overlaid that with, using ERA 5 reanalysis data, the actual vapor pressure and temperature that's generally observed in Greater London during the summer, as well as the Greater London temperature and vapor pressure during two major heatwave events. So the August 2003 event and July last year when the record temperature was set. And what you can see from those specific dots for those major heatwave events for London, the hottest sort of region of the UK, and this is for the daily maximum temperature, very few days at all even register as having slight heat stress or moderate heat stress using these global thresholds, which really sort of underestimates or downplays the significance of heat in the UK, because we know in those events historically that around 3,000 people died between the two together. So we can see that these global thresholds are not particularly applicable for the UK. Another concern we would have with picking out a single value and saying that this constitutes, slight or dangerous or whatever heat stress is that that would suggest that it's not going to change in time, which we don't think is very realistic. And actually, society adapts and people acclimatize, actually you'd expect potentially these thresholds to increase. So based upon this work, we suggest that the use of a percentile based or relative threshold is more important. And by that we mean you'd pick out, say, the top 1% of days and look at the temperature of that, and then you can recalculate that through time, and you don't just pick the same value that was relevant in the period 1960 to 1990 and assume that that will still hold in 100 years. And those sorts of considerations will feed into the open CLIM work that's already been discussed. Get the next slide, please, Rachel. So yeah, the final part of this heat stress work that we looked at was assessing future extremes. So just thinking about it in terms of temperature for now, we looked at how the UK mean temperature scales with global annual mean temperature. So we looked at this UK summer mean, and we looked at extremes. So this 95th percentile of UK summer temperatures. And what we find is that both of those, the summer mean and the summer extremes, warm faster than the global mean on average for all of the different subsets within UK CP18. There's obviously a bit of spread there, but the sort of implications that this would suggest would be if you had an extra half a degree of warming, say between 1.5 and 2 degrees globally, UK summer temperatures might increase by 0.65 in terms of the summer mean, or the extremes could increase by 0.8 degrees Celsius for half a degree of global warming. And next slide, please, Rachel. And then, sorry, the final bit of analysis I'd like to show today was thinking again about changes in heat stress. So this is another plot looking at this temperature and vapor pressure space. In this case, the gray shading is showing contours of simplified wet bulb globe temperature, one of these heat stress metrics. And the colored lines are showing the trajectories for different regions within the UK and how they were at the start of these UK CP18 simulations, midway through and at the end of the simulations. And as I pointed out earlier on, this isn't bias corrected, so I wouldn't use this as a projection of this will be the exact temperature as such. But what we're really interested in here was actually the spatial differences between these different regions. So what you can see is that northwesterly regions like Scotland and Northern Ireland on the left-hand side show a larger increase in vapor pressure and quite a small increase in temperature over the course of these simulations. On the other hand, during the same length of the simulation, more southerly and easterly regions like London on the far right show quite large increases in temperature, but smaller increases in vapor pressure. So we're seeing a slightly different kind of regime between the north and the south of the UK. But actually overall, because both vapor pressure and temperature are important for heat stress, actually we see that the increase in simplified wet bulb globe temperature is actually quite uniform across the country, and it's changing in different ways in different places, which we think is quite a nice and interesting sort of academic conclusion from this. So if I could go to the final slide, please, Rachel. So yeah, just to wrap all of that up, the main things we did, this model evaluation showed that the UK CP18 simulations do a good job compared to CMIP5 models when we're interested in these UK summer heat extreme variables. But we do note that the increasing model resolution doesn't make a huge difference for heat stress variables. We think it's really important to note that global heat stress thresholds are not very suitable for the UK. I'm sure a lot of people already know that, but it's just nice to illustrate that in a different way potentially. They underestimate the risk, and that we think percentile-based approaches would be more useful going forward. And then finally, from the future implications, future projections rather, we suggest that UK summer temperature extremes are projected to warm faster than the global mean, and that there's regional differences in terms of how heat stress might change. And as you might have seen in all those slides, this is currently in review or in preparation, but if anyone's interested, you can please fire me an email afterwards and be happy to get back to you. I'll pass over to Rachel or Jeff.
Yeah, Jeff is next.
Thanks, Alan. So I'm going to be showing 3 distinct pieces of work so that you don't get confused and going one from the other. The first is looking at severe drought probability. These are the same underlying metrics that were used for the population projections earlier. But in this case, it was analyzed in terms of broad land cover classes within the UK. And this then feeds into some of the components of the natural capital risk work. And what we found is that with warming, there's a substantial difference in the drought probability, but also in the maximum months of drought, which we're not showing here, between what is currently classified as agricultural land and what is natural land, and also with urban land. And so with increasing levels of warming, you get increasing probability of severe drought in agricultural and urban lands, but less so in natural lands. And for the UK, this is largely driven by geography, that much of the agriculture is in the Midlands or down in the south and the southeast, where drought is projected to be higher because this is potential evapotranspiration, so you have a higher temperature signal. Whereas with natural lands, a lot of the really large tracts of remaining natural lands are much farther north, so you're getting less drought in that regard. Other countries show different patterns, where other countries may show higher amounts of drought in natural versus agricultural lands. Next slide, please. This is an example of the biodiversity work. This particular is looking at where are refugia, or places where plant communities are projected to be most resilient to climate change. This is a very complex map because it combines both multiple levels of warming as well as land cover change, which is already occurred through 2015. A refugia is defined as any area remaining climatically suitable for 75% or more of the species modeled. In this case, this has undergone an additional layer of elevational downscaling to 1 kilometer. So this is 1 kilometer resolution work. And these areas that are in green, so light green to purple in this case, are areas that are currently classified by remote sensing as natural areas. And so these are the areas with increasing levels of warming, particularly up to 4 degrees C, where the models would project being perhaps least impacted by climate change or most resilient to climate change. And therefore protecting these areas, particularly those areas in purple, you would have, it would be easier to do management. Less adaptation perhaps would be necessary. The areas from dark brown to light blue would also be refugia, but these are all in lands currently classified as being agriculture in this case. And so these would be ideal areas for restoration of habitat. And so when you're looking at something like the Climate Change Committee calling for restoring habitat to store carbon or planting trees, for example, if that's the appropriate restoration, then these areas, especially the light blue areas and the yellow areas, would be those that would be most resilient. And if you couple that with the surrounding natural areas, it's more likely for the biodiversity to be more intact. Next slide, please. And these final series of slides are specifically looking at changes in pollination as an ecosystem service. What you have is a map ranging from a dark spruce green, meaning essentially no change in pollination as an ecosystem service, up to a dark brown, which is a fairly major change in pollination as an ecosystem service, so up to 70 or 80% loss of pollination. The table, the graph rather, shows it for each of the devolved countries. So you've got Scotland, Wales, Northern Ireland, and England separate in this case. And what you find is at 1.5 degrees, England already has the largest potential loss of pollination as an ecosystem service. Next slide. This is expanding significantly by 2 degrees. In our models, at least for insects, we find that insects are perhaps among the most vulnerable to climate change, the most exposed to climate change. They have the greatest impacts between 1.5 and 2 degrees, whereas with vertebrates, with plants, it's more like 2 to 3, and with vertebrates, it's around 3 or higher. Next slide. With 3 degrees of warming, you're already seeing substantial impacts to most of the agricultural lands in England for loss of pollination, but this will also be all of the remaining natural lands. And finally, the final slide. And by 4 degrees, you're looking at potentially areas with up to 70% loss of pollination as an ecosystem service, because this is averaged over the entire country. And so now I'll turn this back over to Rachel to conclude.
Thank you, Jeff and Alan. So just to quickly summarize, so our projections of increased drought and flood risk and heat stress are consistent with earlier studies in terms of at least direction. Obviously magnitudes will vary. Our focus study on heat stress is guiding the development of the heat stress extremes toolkit in OpenClim, including appropriate use of UKCP18 data and choice of heat stress metrics to use. We've developed some novel techniques which Jeff has just presented to assess risks to biodiversity and ecosystem services, which is being taken forward in OpenClim. We've had some engagement with some key stakeholders from the devolved administrations, and all of our work is improving the quantification of future climate risk in the UK, including the analysis of uncertainties. Thank you.